subsystem, which apparently can be built on L1 covenants. For those who saw the bet on X. So that's why chess is a very good example of multi-contract flows. It's still one closed system of contracts for composing all the chess entities, but it's composed of multiple contracts or scripts, and it's not a one giant script that everyone goes through and have to show it at every transaction, but rather it's fragmented into multiple templates or contracts that all compose a nice closed system with a well-defined rule engine in a sense. So that's chess. So I drafted fast with the help of Codex a few webinar pages with a few diagrams which can help. And we also have the draft of your page. I don't know if it's might help us for the beginning. Maybe you can say something about that. What do you think? Then I can walk through code.
Yes, totally.
Yeah, so maybe if you want to share your screen with that so you can scroll.
It will
Then
become a bit tricky right now to do that.
Okay, so I'll do that for you.
Okay, thank you. So this documentation is an attempt to forecast the future landscape of programmability on Cassper after the future hard fork. It aims at present different concepts and how to approach programmability on Cassper. It mainly is designed towards smart contract developers, but also casual developers. The idea is that you can take this first page overview, read it top to bottom, and hopefully you already have enough context to know what are the different building blocks and what you should pick to build your product, solution, or application. And then if you go toward a bit bottom of the document, so there is this simple decision tree diagram that aim at helping you what you should choose or pick first. And then when you go on the subsection, like for different building block, such as covenants or a based app, you get more in-depth overview of what it is, what to expect, when to not use it, and also what good fits or in terms of use case. So yeah, basically this documentation.
I think this session is really gonna illustrate well when to choose covenants. It's actually going to show that the use cases for covenants are pretty broad. So I can't say it's like if you create a complex contract system in L1, it's going to be an advanced task. It's going to take time until the design patterns are going to consolidate and become easier through programming languages, through maybe even some kind of libraries, through SDKs. So it's going to take time for patterns to become clean and crisp and easier to use. But so in that sense, we're still at the stage where we're POCing capabilities. And I think throughout this session, it's going to be more clear what you can do with covenants and when you should switch to based apps. Based apps, we'll say a few words about that, or you can start and then I'll complement you.
Yes, sure. I will give my low understanding overview.
It's not a low. It's more external, which is
external.
Which is how most people see it.
So from my current understanding and how it is stated in the document, you should consider Paste App as a casual application you would write in any language. It's maybe forced to be Rust for this one, and you would have some library that you could import to beneficiate from a larger built-in components, such as an account model and a few other stuff. But basically, you write the logic inside a REST application, and it's
So it's
being
a based app. We call it an app. It's like a based standalone app. So it's not final vbogs. There's no synchronous communication between these applications, but they can be Turing complete. They can be very complicated. Anything you can write in Rust, and they're going to have some kind of ABI or API for developers, or a standard library for. That's what Hans is working on, by the way. Hans Moog. So an API for an account model, and also more importantly and more hard to achieve without the infrastructure, is the canonical bridge. In these apps have their own state, but they can be able to without trust, communicate, take entry, have entry and exit of assets from L1, Caspa, and perhaps other native assets. So that's how you can entry and exit them.
maybe Michael, a few words on the who's the responsibility to run, and maybe provide a larger overview of where will my app be running on.
Yeah, that's like the hard part.
Okay.
To give some like understanding, and this would be like something I would actually need to prepare, to be better prepared on how to present. It's a challenge. Like the multi-contract flows and covenants is like assuming a lot of prior knowledge, and it's like we're gonna jump into something, but these introduction parts are actually harder to do right. So covenants are scripts on L1, and a UTXO can be locked into a covenant, into a script, so it's locked into the hash, some kind of logic. And then when you spend it, the spender provides a preimage of the logic. So it actually provides the full contract governing the spend and executes a spend. So the UTXO model, there's no reading only. You always read, consume, and write. What covenants allow you, by giving the inner code of the covenant, the inner script, the ability to inspect other inputs, the outputs, it can allow you to implement state machines where the input can govern what the output rules are. So it's kind of self-preserving. That's why it's called a covenant. You're entering a covenant in the sense that you're not. So a classic UTXO in a classic UTXO world, like Caspa now mostly, if you're the owner of a UTXO and you decide to spend it and send it to someone else, you can send it to anyone else. The input only enforces the fact that you sign it, that the owner signs it, but you can send it to any other script. And the transaction may have no idea what that other script represents. But covenants mean that the script you're spending can actually say, okay, I'm not enough for me to see your signature. I'm also going to verify who you're sending it to. So you're not the owner, the full owner in that sense. You're not free to send it to anyone else. You can send it as long as you're within the covenant rules boundaries. And that allows implementing all kinds of, in a sense, like contracts. like in Ethereum or a general VM smart contract, the state needs authority from individuals, but it doesn't allow the individual to do anything. So all the time, you can within a contract boundary, the contract can tell you, okay, you can send this to that. You can't do anything you want. You still have to follow the rules. So with covenants, we can simulate and execute the same kind of complicated logic, where there's still there's a rule system and there's no full authority of your UTXO. It still has to follow some rules, and that's how you can take Caspa into something like a chess system and have the Caspa locked in a way that must follow something like a chess rule and the settlement of a chess game. Um, I hope that's clear. So that's when we're talking about covenants and UTXO. So to illustrate, based apps are the point where we implement um, an external application that follows. It's like a based rollup. We call it the based app because it's not a system containing multiple developer registered applications. It's one application in a sense. Okay, so it's a based app that follows transactions on L1, which have a specific payload and a specific subnet. And it executes all these transactions off chain and then reports back to L1 with proof, with ZK proof. So based app is always coupled with ZK technology. Covenants are native L1, don't require necessarily any ZK proving machinery. Based apps are always coupled with the idea of validity proofs and ZK and something like a canonical bridge, for instance, for bridging Caspa in and out of the based app. And it's important to understand that covenants are also the layer beneath the ZK based app. The ZK based app, from the L1 perspective, is going to be also a bunch of small covenants, scripts that govern the fact that the based app must follow the sequencing of L1 correctly, must follow all transactions that target it, must perform exit operations if users demand it. So there's a nice way where the based app is going to use also the covenant system. And that Maxime implemented a full POC of such a based app with ZK with the canonical bridge without Silverscript. By the way, he implemented, in a sense, a scheme of multiple covenants handwritten in script syntax, which is a nightmare and a very big challenge. And it's like you can think of it more of like writing an assembly, in a sense, the bare metal of the system. So that's the POC he finished a few weeks ago. So yeah, I think it helps to understand that covenants are also the backbone of based apps. It's a because the logic of an exit and entry canonical bridge can only be enforced by some smart enough scripts on L1. And those scripts become powerful because they can do a ZK verify nowadays on testnet 12 and after the hard fork. So they can do a ZK verify and verify that the guest program is executing something it's committed to in the right way without actually doing it on L1. So covenants plus ZK provides a very powerful layer. But here today we're going to focus on what we can do in covenant, and hopefully through the chess examples and other maybe a native asset example Ori is going to show, people can get an understanding and get inspired of what can be built natively on L1, and also get a better understanding of how a based app or how the ZK system is built also through these covenants. What's the role of the L1 in this ZK negotiation or ZK protocol between two entities? You must have some. The L1 cannot be just a simple signature verification engine anymore. It has to be a little more sophisticated. So I hope that's a decent overview.
If there are more question, maybe the subsection on the documentation could help. Um, that's
Should I
another point. Yeah.
scroll?
Um,
Scroll it?
yeah, you can scroll or go directly on the left panel to maybe
Where?
governance or based app, as you prefer. Yeah, just each section
Okay, so
carries.
let's
Yeah.
yeah. So let's read this. Start here when the product is best expressed as asset native state on Cassper. Um, yeah, I'd say covenants fit anything that is more peer-to-peer. Anything where there's no like contention around this shared state variable. Like I'd say a classic example is a classic example of not being peer-to-peer is any swap service between tokens where you have to look up the ratio of the swap. So that's usually a single variable, which many read and also write. So it's a contention point. And that's naturally not going to easily map into a UTXO partition state system. But it might be possible. I'm not ruling it out. But a more natural candidate for covenants is what it's things that have a nature of peer-to-peer. Obviously, me paying you, Casper, is a peer-to-peer action, right? Me and you playing chess is a peer-to-peer action. There's only two people involved. So you can think also about financial products that are more peer-to-peer or whatever. So mental model. You want to walk through this because it's more.
Not
I'm not
necessarily.
full.
Just maybe state that each subsection carries a small diagram to trying to illustrate what it does internally. And maybe we could then forecast this diagram into a real execution like the one you did with chess. Obviously, chess will be more complex than just two outputs here. But
Yeah. So
yeah,
the emphasis here is no, I'm just adding one word, the protected, right? The output is protected because it's a covenant, so the output can be the input signature is going to the input script is going to verify the output also follows some kind of rules. So the state of the output is going to have some meaning. The most classic example of following the rules is making sure that the output also follows exactly the same script, only with an updated state. So that's going to be covenant, more or less. And based apps are more like a Solana app, but with the limit that they cannot compose directly in one transaction. Composition is limited, and there was a reason VPROG's design, which is going to take longer than this coming hard for. The VPROG design is achieving something hard. So obviously we cannot achieve that. What we could do is build a roll-up system, but I'm not sure we want that now. Okay, I'm going to switch to this one. So I want to say something about Silverscript. I feel like Ori left me at the altar, if that's the right term. Like he didn't show up. I don't know where he is. Maybe he's planning to show up later.
I can contact him on the side.
That's okay. Yeah. So you think we should do a fast Silverscript overview?
We could. I think it's interesting. At least explain what it is and how it is related to covenants, maybe?
Yeah, so maybe I think that can happen through the examples. Like I can go directly to so ICC is what we call intercovenant communication. I'm hoping Ori is going to talk about it, but we should, before talking about intercovenant, we should speak about a covenant.
Is coming in a few minutes.
Okay. So this is somewhat advanced, but the example is simple enough to show silver script and to show covenants, I think. So you know what? Let's wait 1 second. All these examples are not so, there's no like logic to explain. There's like more like compiler tests than interesting examples here. Okay, yeah, this one is a good one. So this one is, from what I see, it looks almost like a native asset, like right. So you have a covenant, a contract, and you have fields here that represent the state. So each UTXO belonging to this covenant would be actually a compilation of this contract compiled with the value, the amount value in this case embedded in the state, embedded in the contract, like a constant in code. And this covenant is trying to validate that.
Hello, can you hear me?
Yeah, we can hear you.
Yes.
Welcome. So I'm still presenting only the basics of Silverscript and a covenant. So feel free to interrupt. Actually, because I'm presenting your creation. So you're going to show, Ori is going to show a more complete native asset example, but this is like a basic enough. So basically these commands are making sure that we go through all covenant affiliated inputs and covenant affiliated outputs. And we make sure that the sum of values and the amounts of the outputs is less than or equal than the sum of values and inputs. So basically, if you just had encoded like an amount field in some arbitrary covenant, it doesn't represent Caspar, obviously. Our Caspar value is something else. This is just a field within the state of a covenant, saying basically nothing. So if the covenant doesn't, if a native asset like covenant doesn't enforce value preserving, meaning value cannot be created by thin air unless there's like some kind of special minting logic, then it's not a real asset. So I would say this example is illustrating the most basic law of preservation of value, and not to invent value from thin air. So it's basically going over all the inputs and outputs associated with this covenant, summing all the inputs, and making sure that all the outputs, the sum of all outputs is not more than the sum of all inputs. And there's a few very specific opcodes and built-in functions used in this example. Essentially, op input covenant ID allows you to read the covenant ID of this input. Then you can read how many other inputs, including myself, belong to this covenant ID. In the system, you write it in a way such that it makes sure that every UTXO, which has a specific covenant ID, also follows the rules of that covenant. So here we read the input count, the output count, and for each of the inputs and outputs, we sum and verify like the value preservation. So that's a basic example of Silverscript and a covenant. The hidden pieces here are, so Izio, you know this, you know the role of validate output state?
I think I do. Let me try to explain what it does, and
Yeah.
Hori or you can bit me later. So validate output states verify that the transition to the next state is correct. Essentially, you call this function and put the new state you want to be into the covenant for a particular output, and it ensures that the new state is the one you declared.
Right. It also does something like the hidden part is where it verifies that this output is committed to the exactly same script we're running now. So that's like a reflection kind of logic. When you write validate output state inside a contract, it's going to make sure that this output at output IDX is following exactly this covenant we're running, and its value field, the state, is what we write in the output amount. This way, that output, when it gets spent, is also going to verify this value preservation rule, because it's self-enforcing. Like the rule.
Can you hear me?
Yeah, we can hear you somewhat. You want to try and talk?
I think he doesn't hear us. That's the issue.
Okay, so I'm gonna go on for now. Yeah, so that's the magic like of this. So two roles, validating that the output follows the same covenant rules we're running now, and the update of the state is coherent with what this rule system enforces. Read input state is like kind of the other side of that, saying, okay, when we run this contract and this input, so and a contract runs for every input, right? That's how UTXOs work. There's a script for each input and it runs. L1 is going to run it. So we obviously give access to the state of this input in this form here. So when you inside the logic here, you can actually read the amount field directly. But when we're looking at other inputs, which share the same script, we have a special command for that. Read input state is going to return the same state object of amount from the other input. That's how we can do like a many-to-many transition. It's not only a one-to-one or one-to-two. So actually we can look at a group and we can look at a group and validate the logic of the whole group, how it transforms. So that's what a native asset is a classic example where there's always going to be some kind of many-to-many transformation of value of that native asset. So you're going to have to validate all the group at once. You can't just look at one input and some specific outputs. You have to look at the whole subset of inputs, outputs belonging to this covenant. Now, because this is a complicated scheme, we actually designed macros, covenant macros, to automate this. So probably I should.
For those who maybe didn't understood what it means, when you invoke a contract on an input or that is part of a transaction, you could have several inputs that are related to the same covenant, and so these two functions, primarily the read input state, make you available to access others' input state. And when Michael said in native asset this is common, for example, when you want to transfer a native asset and you have two UTXO related to this native asset, each one of them has 10 amount of this token, you want somehow to consolidate the two UTXO, so 10 plus 10, 20, and output 20 to someone else, for example, or to yourself.
Yeah. So in order to automate, so we saw this is relatively complicated. We have to write all this glue, reading inputs, outputs, doing this, it's this. So we wanted to automate this so it's easier to write secure covenants without making mistakes. And that's where the covenant macros come in. So you put on a covenant macro. This is a more explicit form. You can actually just do something like covenant singleton, meaning I'm doing a one-to-one, covenant one-to-many, or just from two. And the compiler is going to infer the correct shape to generate, essentially. So in the case above, instead of writing all this, you can actually just write the verification logic, meaning you write a function that accepts all the previous states from all inputs of this covenant, all the new states of all outputs of this covenant. And here you only have to do the sum and verify that the value is preserved or something, or verify a signature or whatever. So you do the verification logic in one place, and you don't have to do the plumbing of inputs, outputs, and verifying all that. So that's what covenant macros are for. Another example is
So this is a sugar syntax to avoid writing a lot of painful lines, and this essentially express the same needs, but
yeah, I just want to
simplified.
see yeah, here. So essentially, as a programmer, this is what you're going to need to write. This is my contract matrix. I'm having two values, and this is the step function. And I verify the prev states and new states and args, any arguments I need for the verification, and I can verify my logic here. And actually, the compiler is going to generate all of this. It's going to do to implement a leader verifier, which actually reads all inputs and all outputs and expects all outputs, and calls the policy step you write at the right place. And it's also going to have an automatic entry point. An entry point is like a main entry points of a contract are like main functions of think of it as if you have a few main functions and the first command line argument telling you what main function you want to run this time. So you have three inputs, and so only one of them needs to run the full validation because it actually reads all the other two as well. And the other two only need to make sure that the leader exists. So they do so by saying, I make sure that my index is not, that the first input of this covenant is not me. So one of them must be the first input, and he's going to have to run this logic. So that's basically a lowered form of what we do with covenant declarations. And now I'm going to show you chess and show you how I broke all these declaration patterns, and we need to generalize them better. No, it's an extension of them. Ori, can you
Maybe
speak?
we want to go over the simpler native assets example first.
Yeah, so take the screen.
If I succeed,
Explain native asset, I think, but frame it with ICC, right?
yeah. I'm trying to, okay. Now it's possible.
We have
Uh,
many survivors in the staying online.
yeah. So I hope my demonstration will be simple enough. It's not a very complicated construct. So the purpose of this contract is very basic. Is to establish a way to transfer tokens and mint tokens, native tokens as part of the Casper network that are validated by miners. I called it for now Dog 20 because there is a standard called Cat20 based on the ERC20, but I'll probably change this name later. So if you want to transfer a token, it's very basic. You need very basic things. You want to check that you collect the tokens from a few UTXOs, and you send the output to several recipients, and the contract needs to verify that you didn't print any money. So this is the main entry point, the transfer. As you can see, it first it gets the previous state and the new state as a parameter, and it validates the state transition. So first it checks that the signature is right, and namely it checks that the owner of the tokens that is specified in the previous state has the permission to move the money. Right? So you check it by checking the signature is correct. This can be seen here. I'll explain maybe later about different kind of signatures, but the simple case is public key based signature, and this can be seen here. So check sig is just the shortcut for check sig, which checks Schnorr signature against the public key of the previous owner of the UTXO.
So each input state has to be verified for its owner.
Yeah.
Can you explain the for a second?
Hmm?
The force. Why is the for so weird? 4 arguments. Line 12.
Yeah, I'm not sure if you went over it before.
No, I
Because,
didn't. No.
Huh?
No.
So basically, in a regular programming language, you want to go over range something like this, right? You want to go from with I from 0 to overall prev states, right? But since the script language of Caspa is not Turing complete, it has no native loops. So what we are basically doing is taking the maximum amount of iterations and hardwiring it inside the script.
It's a
So
loop unrolling.
yeah. So basically, this is translated to something like I equals 0, and then I equals 1,
With the condition.
before each code we check if I is smaller than the maximum amount of iterations.
No.
Hmm?
No, you check if it's smaller than the actual amount.
Sorry, yeah.
So you unroll according to the constant max covariance. You dynamically check by the actual runtime.
Yeah, and we're doing this until I equals the maximum number of iteration. So
-1. Yeah.
So what happens is that the script actually contains all of these iterations, how they coded. It doesn't contain any or something similar in with opcodes. It actually contains all of them, and some of them will be determined to be redundant when this condition will become false. All of the rest will be falsified as well. So yes.
Yeah, so that's
Yeah.
the story why for loops have also a fourth argument.
Yeah.
For
So because you can't know you can't bound it in runtime, so you have to put an upper bound in compile time. So this is why the first two parameters can be calculated in runtime. For example, first state.length is computed on runtime, but max covariance is a constant that is known in compile time. Here in compile time, you can set it, and
so everything on the top line of the contract is are constants.
yeah, this is like definable contract constant. When you compile a contract, you can decide what the value of this parameter, and then it is stayed permanent for the rest of the lifetime of the contract. So I hope it was clear enough. So check amount is a little bit simpler. By the way, I didn't mention it before, but there are some entities that are called minters that are allowed to print money. For some contracts, you can set it. You can just set an initial amount and then allow no minters, or you can decide if you want to have some minters. So obviously, if you're a minter and you're allowed to print money, we can skip the check amount verification. But otherwise, we are counting all of the amount that exist in the previous states and checks that it sums out to the same amount that exists in the next state. Mm.
What verifies the distribution of outputs?
What do you mean?
Like, why am I as a user safe in terms, like, so the contract enforces value preservation, but I just want to emphasize that by signing as a user, you agree to the distribution of outputs. So all the inputs owners actually sign, and the signature also encodes all the outputs. So by signing, you actually agree to exactly how the outputs are distributed.
Yeah, sure. If it wasn't clear before, so each state, rev state and new state, is associated to some input or output, respectively. So when you sign the transaction, you usually sign all of its outputs. So you implicitly also sign all of the state of the output. So by verifying that the signature is correct is the different way to verify that the user agrees to the new spread of tokens.
You want to say a word about line 50? I explained it just before you went on, but it's kind of the magic part here.
I'll let you explain.
Yeah, just what I said before. The previous states and new states are not just born of thin air. The compiler is going to generate the full code we saw before that reads all the prev states from the other inputs and verifies that all new states are encoded in the outputs. So that's compiler is going to generate code that connects this and tell us these are really the states in the transaction inputs and transaction outputs, and we only need to write the logic to verify the transition function.
Yeah, exactly. And the prev state is not an actual argument that you can just inject as a part of the signature script. It's something that is just a virtual argument that the script actually reads from the other input, the previous UTXOs.
Yeah. Essentially, the script itself, the inputs for the script itself coming from the signature script, what are only the two last ones here? Maybe explain what witnesses are.
I'm not sure this is so important, but maybe we'll just try to explain what are the other types of signatures. So
if you want to say like if you want, I made like in my book, I made a page about ICC. If you want, I can show that and you can speak about it more abstractly first.
Whatever you prefer. Okay,
also do it
maybe
afterwards.
let's try out your book.
Okay, let's try. If it doesn't help, just we'll go back to this. But so stop sharing. So I can read this out loud, or you can use. So intercovenant, the way I saw it, like the intercovenant communication can sound like, okay, in covenant is sending a message to another covenant, but that doesn't really have a meaning or a well-defined meaning. What we understand ICC is more about I'm a covenant and I'm authorizing a message, or I'm authorizing an action on another covenant. I think you should, yeah. So one way to do that is to say, okay, I'm a covenant. I'm running on some input A. Input 1, I'm covenant family A. I have my own logic. Input 2 has his own logic. We're in the same transaction. So through my code, the code of A, for instance, the DOG20, can have its own state remember that the owner is covenant B. And then it can simply verify that there's another input in this transaction owned by covenant B. And it's essentially going to say, okay, I trust covenant B. Covenant B declared itself as an owner to me. I don't need to know what it's doing. Its owner chose to trust it, so it knows what it's doing. So I'm just going to delegate the authority. If I see another input of covenant B, I know the transaction is not going to get accepted unless that input is going to be processed correctly. So by seeing that input, I can say, okay, that input is authorizing also my transition function. So that's the pattern. I think the basic element of intercovenant communication, and it can be. I think it's a powerful idea.
Maybe I'll try to demonstrate it with a simple example. We'll get back to the dog20 script, but I'll try to make just a short explanation before it.
You have so until you get to that you're going to get it on screen. I'll just say that an example of a covenant B can be the rollup, an app or a ZK rollup proof transaction, proving the execution of a rollup batch of transactions and the exit of some native asset to someone. You can think about it as covenant A is not going to execute covenant B within it. It's only going to check it, delegate the authority. So in a sense, so it's not, instead of nested covenant execution, we get like side-by-side execution where one can look at the other.
So maybe we will demonstrate it with a simple example with native tokens. So I'll try to explain briefly what we are trying to achieve. So let's say person A has 50 tokens, some tokens, and he wants to transfer let's say 20 tokens to B. So how do we achieve that? So the easiest way to achieve that is using a digital signature. If A has a public key and B has a public key, so A is using his private key to sign a transaction that authorizes a transfer of 50 tokens or 20, whatever. But what are we going to do if A is not simply can be represented by a public key, but is a more complicated entity. For example, a company that controls tokens via a multi-sig contract. So how will we sign it? And if we only want to support in the Silver script contract only one type of multisig, so we will just hard code it in the in the contract. But if you want to allow any general contract to own tokens, so it's not very intuitive how to do it. One way that comes in mind is if we could just store inside the same way that we associate token to public key, associate it to a contract, and then evaluate the contract inside. Let's say A is a P2SH contract or some multi-key. And we have, so what we would theoretically do is make doc20 evaluate contract A to prove ownership of the tokens. Yeah. So so we want to enable to let the doc20 contract execute some arbitrary logic inside it. But this is pretty problematic in a script language that is not intended to be Turing complete. If you allow arbitrary script execution, so this becomes very quickly Turing complete. And this exposes a lot of dangers and very hard to monitor and compute gas consumption and etc.
Ori, just 1 second. We got a request to increase font size, if you could, on the VS Code.
Just a second.
Thank you.
No. I hope it's better now. So it's impossible for doc20 to execute some arbitrary code. So instead of that, we are using what Michael called ICC, inter-covenant communication. We are proving that A is aware that his tokens are used. And the way we are doing it is by we are making a doc20 transaction with one input that spends UTXO that is owned by A. If the transaction has an input that spends UTXO that belongs to A, this is a proof that A is aware of this transaction and authorizes it. So it doesn't matter what is the logic of A. If we have some input that belongs to A inside the transaction, so it means A saw the transaction, signed it in whatever way that A signs transactions, and he's okay with the result. So now we can see it here. For example, in we have several owner types. One type of owner is a pub key. we talked about it before. This is the regular type, and you can spend money by signing a Schnorr signature. But with the identifier script hash type, this is like a general contract. So we are validating that there is some kind of an input that belongs to the contract. I mean that belongs to the owner. Here we see that the perf state is owned by some contract SPK. So all we need to do is see that there is some input that spans a UTXO with the same SPK. And here, in order to save scanning all of the inputs, we allow the spender to
To save
attach
what?
a witness.
In order to save what?
So our goal now is to see if there is some input where it's script public key is SPK. So instead of doing some kind of for loop, I'm writing in pseudocode now. So I in 0 to something like so we could do something like this. Check if we have some input that spans this UTXO, but this will be very costly, going over all of the inputs, and theoretically in each iteration. So this can be this can have a quadratic cost. So in order to save it,
Quadratic script size cost.
Yeah.
Because it's unrolled.
in order to save it, we ask the spender to give us a hint where to find the said input. The hint is provided in the witnesses array. So we just once we check the relevant perf states I, we just check the relevant witness I that is providing us the exact location of where to find the relevant input. And this saves us the scan, the very costly scan.
I'd say just add like a comment that it's I see it as an example of the way a script writer needs to think. Verification first. If you can avoid a sweep by hinting something, kind of it happens also in ZK circuits. You provide external witnesses. Like in ZK, you can have if you need to, for instance, to compute the square root of a number. So the square root algorithm is relatively complex. So instead, an external entity can give you a witness of the square root value, and you only need to verify within the ZK circuit that if you apply power to the 2, if you multiply that hint by itself, it produces the original value, so you're good. So this is kind of the same. You want on-chain scripts to get hints and not need to do a sweep.
Yes. Yes, for anyone who is familiar with computer science theory, this is an example of how we usually solve NP problems, where finding a solution is very hard, but once we have some hint, it's very easy to solve. So I think this is it. Izzy or Main, do you have something you want to ask about it, maybe for some clarifications?
So I had the privilege to see this script earlier, so I'm a bit more familiar. Maybe I would just add for other less experienced, like I was a few weeks or months back, that just to make it sure, we have different kind of address in Cassper. Like Ori said, the classic or usual one is the identifier pub key. Here it's a casual keeper secret key private key, and you sign with your secret key over the input and output on a transaction. And the silver script that Howie showed here, it's checking the signature, so to verify that the owner agreed on spending. But the other one is maybe a bit less common. It's representing an address that carries, or let's say summarize the representation of another script, another contract in this context, so or covenant.
Yeah, and generally, yeah, this is divided to two types. We have script hash with it, which is stateless script, and covenant ID, which is a stateful script. So you can also associate some tokens to covenant ID, which means now it's not only that you can have some simple multisig. You can have a very complex logic that depends on changing state. So one example of it is how, for example, I guess that in the near future, we will want to bridge tokens from layer 2 to layer 1 with some kind of base rollups or reports. So the base rollup it will be managed in L1 by some kind of covenant with updating state. So when someone will want to transfer some tokens, something like USDT or from layer 2 to layer 1, he will not just want to, he won't always be able to withdraw the money. It depends on the layer 2 state. So in this case, layer 2 will own some of the tokens, and just like in a UTXO, using identifier covenant ID, and it will in the layer 2 rollup will only allow to attach an input to a transaction that spends it only if the L2 state has the correct state that allows the spending of those tokens.
So you're saying that the other contract, which is giving the authorization, the other covenant has to know about this covenant. Like this covenant can be, the DOG20 covenant doesn't need to know what's the entity and logic behind the other one, but the other one, if it wants to to do it correctly needs to be aware of this covenant. So it's the relation
Yeah.
where one of them needs to know about the other.
So here, for example, A can be some I don't know, Igram or Casplex, yeah. So so these 50 tokens are represented in the L1 by just one UTXO. But internally in the rollup, they can be split by any way that depends on the internal L2 state. And A will allow L1 to spend it only if someone brings a ZK proof that shows that inside L2 he has the correct balance. Okay, I think we can finish with this example, and we can go on and for Michael to demonstrate his chess example.
Maybe I can jump in and just say a quick implicit assumption that maybe some people do not understand, that it took me a while to also understand while looking at this example, that the verification of this pay to public, pay to script hash, the verification was simply making sure that it is part of the inputs to the transaction and nothing more. And this is sufficient because the spend of the entire transaction is atomic. It means that it either works for all inputs or fails for all of them. So it's sufficient to just verify that one of the inputs is the script, and then we can know that if the transaction passes, the script also is spendable correctly.
Yeah. Thanks for that, and jump in whenever you want. You want to introduce yourself?
Sure, yeah, Manyfest, and I'm following those guys, and I'm like easy. I'm like taking my slow steps behind those guys that are developing very, very fast, and I'm slowly trying to grasp those ideas, and it takes a little while, but I'm trying to also share what I'm learning from them. So if you have any questions, you can ask in the chat, and I'm available there, or everything everywhere else. And yeah, thank you.
Great having you with us. Okay, I'll go back to sharing that screen. So I wanted to talk. So ICC was about covenants not knowing about each other, authorizing one another, or one of them knowing about the other and the other treating it only as an authority. So that's intercovenant. I want to speak about multi-contract flows within a single covenant. Like a covenant can be thought of as a system. And if we speak about chess, so it's a system where you have a league, and the league can allow players to register, and players can start a game, and the game advances, and it settles and updates the ratings of both players. And all these entities are within the same covenant logically, but it's a multi-contract system within the covenant. And the examples, like the example we saw of DOG20 is a single contract. We only saw one contract, and the logic is self-enforcing. Like each input is going to verifies this contract, and it's also going to verify the output are following the same contract. So when they are spent, they're also going to have to prove they're spending correctly, etc. So it's a single contract, and it's a little simpler. And here I'm going to talk about multi-contract flows. The reason we need multi-contract is because every spend of a contract actually has to be, you have to provide the full contract script in order to prove the spend. If you just make one contract bigger and bigger, eventually it grows out of the limits of a single transaction. You can't really ever use it. So what if your logic is complicated and fragmented, meaning you don't really need all the logic all the times. You have some kind of branching, and you have different entities with different roles in the system, and they don't all need to share the exact same logic and code. So how do you do that? So some people might be familiar with Taproot or MAST, Merkleized AST, I think, or meaning a script where you can actually branch on different pieces of logic without revealing the full script for each execution, but rather only revealing the parts of the script that you need to show. Like if you have an if-else branch, so you only need to show the script body of the if, and you don't need to show the code of the else. So you can actually have like a Merkleized execution path. So that's a common optimization in many systems. But here I'm talking about something a little more broad. Sometimes you want the scripts to have different roles. So there's not necessarily only a branching system under one large contract where it's not only an optimization where you can reduce the number, the size of the script you need to reveal, but it's more about different roles in a system, like the example of chess. It can also be relevant if, for instance, in the DOG20, if the minting logic is more complicated than just printing money, and that logic is big enough, so you might want to split it to another contract, but still live under the same covenant. So you can use the same concept for a minter vs just a user and a native asset system. And you can go on with this with several examples. So here I wanted to start with actually what I call the multiplexer pattern. So I think about it as a design pattern. So Ezio, I think this is completely new to you.
Yes, correct. Completely new.
So you must help me explain it. Hope.
I'll try my best. I promise.
Yeah. So So multiplexer started when I was starting to think about a chess game, a full on-chain game of chess, and the rules of chess are pretty complicated. The board can be complicated. Every piece can move in a different way. You might need to sweep and ask and check whether this tool can move or not, and make sure there's no check threat because of a move. So the logic isn't easy. If you just do things like go over the whole board and check something, you'll have a for loop of 64 iterations unrolled and compile time. Not a good idea. So I was starting to think about how can, so basically, I was talking about this with Ori actually, and he said, yeah, you know what Taproot is? Actually, I think ICC can simulate it. So he called it Zen ICC. Now I'm calling it something else. But essentially, he said you can have some kind of contract that is the multiplexer. It actually only chooses the next piece of logic to execute on the following transaction. So kind of an ICC where we actually delegate some of the logic to a neighboring input, but here you'd have to make it like more of two transactions. So, you know, if you have a DAG, which has 10 BPS, you don't really worry about submitting two transactions. It can still happen pretty fast, I think. And other systems where you might have to wait longer if you have two transactions. So you can split the logic and have this kind of a multiplexer which selects what next logic to he wants to execute, and then it sends the state to that worker, call it worker A, and then worker A is going to spend that according to his own rules, and return back and then go back to the MOOCs. Does that make any sense, Ezio?
Yes, totally. And I already have one question, but I'm sure it will be answered later, so I stay quiet for now.
Okay, so the pattern would be that if I look at, so it's the branch under my Silverscript fork for now. I had to develop like a few compiler level stuff throughout, which are now in a PR. So let's just look at this MOOCs. Look at the state in a moment. But what I want to show is, so I'm calling the main entry point route, and one of the arguments it accepts is a selector. So the user is telling me I want to multiplex into worker A or worker B. He's either going to pass 0 or 1, and the multiplex logic is simply saying, okay, so we're going to have two more contracts, A and B, to the left here. They're all they're going to have the exact same state layout. They're going to have these three fields, which I'm going to explain, and they're going to have the value. In this case, a very simple state. In the case of chess game, it's going to be like many fields representing the state of the game, but here it's just a value. And the multiplexer is saying, okay, I don't know how to execute logic A or logic B. I'm letting the user select which one of the logics wants to execute. If it's 0, I'm going to have the target template. Target template is kind of the hash of the contract. So I'm calling it a template because it's not exactly the full hash of the other contract, because the full hash of the other contract includes its own state. So the template is the hash of that contract without the state part. So it's the immutable part of the contract. So that's why I call it a template. And it's a stable identifier. It doesn't vary. So based on the selection, I say, okay, I want to go to A. If the selector is 0 is 1, I want to go to B. And then we have a special, then I compose the state I want to move into. And it has the same templates and same value. So the state isn't changing, but I'm passing authority to a different script essentially now. I'm validating. So instead of what we saw before, which was only validate output state, and it only received an output index and a state, and it verified that the next output has this state and this script we're in now. The validate output state with template is saying, okay, I want this output at index, output IDX, to have this state and to belong to this template. So it's a built-in function, meaning it's like a compiler understands this statement in a special way and generates like a series of opcodes verifying something more complicated. And what it's going to verify is that the output script I'm sending to is actually obeys or is part of this template script. And it's going to, for validating that, it's going to use these witnesses we're bringing here, which are the part of the contract, which is the prefix before the state and the suffix after the state. So it's the constant parts of the contract. So when hashing them, you're going to get the template, and you can verify this output is actually that template. So the multiplexer is essentially saying, my job is to verify that you're sending the authority of spending to the correct worker template and not just any script. I'm verifying it being sent either to A or to B that I already know. You don't get as a user to send it to anyone else. We're staying in a closed system of scripts. We don't open it widely. Then A and B are essentially the same. They have the same state. A is going to do just some kind of logic, going to recompose the state, this time updating the value, and then it returns to the multiplexer. So it's updating the state and going back to the MOOCs template. You have a question about this, maybe?
Yeah, I have one. I see we redefine the template at this stage from A or from B. I assume we do the same. Is this a requirement? Like, is it envisioned that we could somehow at this stage swap the templates?
What do you mean swap?
Like line 26, 27, is it expected that in some context this would change?
No.
No, okay.
So and as a design pattern, the templates. So here's the challenge. I wanted you want to design the system, but how do you? So you need MOOCs, right? You need the contract of MOOCs to know A and B, right? It needs to know the script. Essentially, it needs to know the script itself or a commitment to the script, right? So MOOCs needs to know A and B. If we had A and B embedded into MOOCs, besides the obvious size problem, but if we had A and B hashes embedded into MOOCs, but then A and B also have to know MOOCs, so they have to embed the hash of MOOCs itself. And that's going to create a hashing cycle, which is unsolvable. So essentially, we have to create it in a way that the hash or the template of a script doesn't include the other templates. And the other templates get injected at Genesis. Genesis is like the initialization of the covenant. So the person initiating the covenant family can show everyone else, and it can be easily audited that it was initialized with the right templates that correspond to the actual contract in the system. So in order to avoid cycles, we have to get all the templates injected. So that's why A essentially can know A within itself can know what A template is, even though you would say, how can it be that A knows itself? That's because the template doesn't include the field, so the field can have the template. So as a design pattern, there's these these fields in the state are immutable, meaning we want all contracts involved in the system to always pass them as is, because they're like the identity of the system. Otherwise, you probably break the logic somehow. If you want a state machine that doesn't run away, it cannot go to some arbitrary script logic. If you want it to be closed, you have to have the knowledge of all other templates, and you have to pass authority very carefully. So the pattern is you're always going to see the template part of the state passed as is, and the state can change depending on the logic of the worker. Does that make sense?
Yeah, that's really interesting. I never thought of it. And can you imagine even, I'm pushing the concept even further, but can you imagine a mux that invoke a mux, and so you could create some sort of, I don't know, sub-workers and weird architecture?
You'll see in the chess already a lot of like complexity. There's places where the MOOCs routes to itself, or at least at some stage I had that. So the game itself, the chess game itself, is implemented as a MOOCs and several workers. But then you have above that game a bunch of more entities like the league and a player. that I mentioned before. And that's where the contract split is not only about efficiency of execution, it's also about roles and the composition of roles in one system. Should I show the code through VS Code? Would that be more clear? I might probably.
Maybe another perspective. Tell me if I'm right, but we can look at it like a router which have 2 slots, and only while deploying this router we can put in the slots of the 2 different functionalities. We can put whatever we would like, and
you mean the injection
those
part?
slots.
Yeah.
Yeah. So yeah, when I think of it, like there's 2 slots there, and I just need to commit that the slots are working with each other, but only it's general purpose, and only while deploying this, I need to specify the exact logic of those slots.
Mm-hmm. Oh, you see my VS Code? Yeah. Showing this. So chess is here. Pick one. Right. Pawn is actually the more the in terms of like the moves. So some of the workers are named by the piece, the king, knight, and some of them are named by the move type, horizontal, diagonal, vertical. That's where the queen and the bishop or whatever share the same kind of movement. So you can share logic. The verification of a diagonal move is equivalent to the bishop or to the queen, or a vertical and horizontal move for the bishop, for the rook and the queen. So that's one. So pawn is actually one of the largest contracts, and that's because it has a lot of special rules, like the en passant and become promotion, capturing the opponent is also a different move. So there's also all kinds of complications. But we should probably not. Okay, so this is like a script with almost 300. So this is only the pawn logic, and this is I don't know, 350 lines. It comes out to be approximately 2,500 bytes, so more than 2 kilobytes. And if you put all the logic of the chess game in one script, it doesn't fit into limits. It's also very inefficient because the full contract needs to be revealed at every step, even though you only execute a very small part of the game. So let's look actually at MOOCs first, because that's like the hub. So naming convention, template field, carry template selectors, hash side values, not text. So template, like I showed before, it's an idea of another contract. So, and these are the status has a few. It's like an enum, castle rights, passant index, pending move. I'll explain. Okay, so actually, that reminds me, I should explain the limitation of MOOCs here. So can you, or would you, or one of you want to try and show where this system would fail? The simple MOOCs AB. So I don't want to, yeah. So
I would say when you
I,
hit the limit, but you need to have very much.
yeah, I didn't show enough. It
Yeah.
didn't show enough for the riddle to make sense. Because obviously a toy example, so you kind of don't know what I mean because obviously it's not doing much. So like there's no objective function. There's no like doesn't do anything, so you can't tell me where it fails. But where it fails is that assume the condition would be essentially someone can do the switch from the mux to A, but in a way that A cannot execute. So it's, here it doesn't. There's no real condition checked. But I don't know if A had a requirement not about the arguments but about value. It would say value must be lower than 100. But that's actually just do that. So if someone had state value, someone would be at MOOCs and had value 50, and then it would apply selector going to A. So this, essentially he makes the system is now stuck, right? Because the value is 50 and it must execute A. That's the contract owning the UTXO now. But however you try to execute it, it's always going to fail because the value is not going to change. So it's like a essentially the transition function is supposed to execute across two transactions, right? So as a designer, you have to make sure no one can make you get stuck in the middle. Normally, if a transition function is implemented in one atomic transaction, it either executes or not, right? But here you break it into two. So you have to make sure that that cannot allow anyone to make get this UTXO stuck forever, meaning making a selection which is invalid, but then you actually performed the transition. You already authorized contract A, but now you're stuck with A forever because A had this requirement of value less than 100. Oh, yeah, I was reversing it. I said 50, yeah. So the requirement would be that value is greater than 100, so it never fulfills. That's what I meant.
Do you need then to systematically duplicate the validation, like prior selecting the target, in this case A?
So it's hard. So in chess, so there's two ingredients that become natural when you look at a real scenario. And the ingredients are, in the chess case, there might be other patterns one can implement, but what happens in chess naturally is that at the first move, so obviously there's two players and they both have a pub key. So no one else can, when it's my turn, only I can play. And in order to prove I'm the player, I have to sign. So what we do is in MOOCs, in the chess MOOCs here. So we first verify, of course, we verify the signature according to the turn. Then the player is going to provide the move, okay? The actual move it's going to do. And we're going to inject the move into the state. We're going to map it into the one-dimension index space, 64 board. This is going to be the pending move. And essentially, the user has committed to that move. And then the user also tells us we trust him because it's his problem. What's the selector? He's saying, I'm moving a pawn. So 4 mix from Y is a square holding a pawn. And the selector for that is the pawn contract. And we don't even need to verify more because there's two ingredients. One is the commitment. Now, what happens if the system gets stuck? If he made a wrong choice and there's not really a pawn in that square, and the pawn contract is going to verify there's a pawn in that square and it's going to fail, right? So what we do is use a timeout. So because chess is anyway a game where you have to time out a move, so we obviously also have to defend against the fact that the player can stop and stall the game and not make a move, even when mooks. So we need a timeout mechanism anyway. So essentially, that's the combination. If you committed to something and you cannot continue because of the rules, that's your problem, and the opponent is eventually going to claim timeout. Because you're essentially stuck with that UTXO with some specific DAS score, so I can prove the age has passed long enough, and then settle the game back to the settlement point. So I'm not sure about, yeah, so I think there's some kind of pattern emerging here about commitment. Like if you leave the stable state, you have to commit to that and take responsibility if you cannot complete the move. That's I'd say that's what. So essentially, in every contract here, you'll see at the end a timeout entry point, where the opponent, actually not even the opponent, it's a permissionless call. You don't even need to sign. You just say age is too large, and then according to the turn, we give the win to the other side.
So in this example, I understand perfectly. In another example, could there be a way to roll back to the previous state, whatever it was, or with this method, is it not realistically representable or expressible?
So there can be. So you'd have to give me an example, and then we'd analyze that example. There can be there's some path I avoided because it's very delicate and I didn't need it. So that path is a path where you can verify at the multiplexer sufficient enough of the conditions, not all of them, but enough of the conditions to know. Essentially, it means it's a pattern where it's unfailable, meaning there's no require in the worker. It only computes the transition, and you can allow that if you make sure enough of the conditions in the original place. You know what I mean? So if MOOCs would verify that it's the source square has a pawn and the type of movement, I don't know, it would verify enough such that the pawn move can be executed, enough to make sure it cannot be stalled, so then that be okay also. But it's a delicate, like you have to really close all possible paths. It's not so easy. The other option it depends. I mean, going back to the yeah, you can all. I'd say you can leave. I don't know. You have any example in mind?
Maybe something even more simple. I'm representing a coffee machine, so I put some coin in the insert zone, and wrongfully I put in a coin that was not supported, like 20 cents, and the machine only supported 50 cents, I don't know. So this simple state machine of serving coffee. In this case, would you say that we would prefer to validate the transition in advance and not allow the system to be stuck? Or is there
either that, or because it's easy enough to, in this case, I would say the owner of the machine can have a signature, and all the worker contracts can have an entry point receiving a signature from the owner saying, okay, go back to MOOCs and go get back the coin to the user. So it's really it really depends on like the use case, and then you design the solution. I feel like every problem or every kind of application would have a slightly different solution, but it's going to be a natural one, not a forced one. So yeah, I wanted to, okay, so we saw this. You see my the diagram? Okay, so inside the game, there's two special, there's the MOOCs, which is the terminal, like the main hub, which all the moves start from and go back to. And then there's the chess, the settle, the terminal like point. And it has enough complicated logic on its own because it's going to consume, when you settle, you actually consume the two players, update their stake. You take the stake from the game and give it to the winner, or split and draw, and you update their ratings. They have a rating. So that's like the MOOCs. So you have all the workers. So MOOCs is going to multiplex into a worker, and then the worker is going to go back, or go to the settle if it's on a timeout. And when the game ends like normally, so you go from MOOCs into settle. So that's inside the game. Now I'll just show you for a minute the auto contracts. So you start by a league. I'll show you the code. Oh, okay, so I should mention, we spoke about templates. So what I did here was so this is the area of templates. Here. I'm just seeing something I didn't remember. Anyway, the game itself doesn't need to know what the league template is. The game itself is never responsible. Yeah. There's some detail I forgot. Okay, so the game, that's a good example actually. The game, so there's a system of multiple contracts, and not all of them need to know about all the other contracts. Essentially, if you think about this as a state machine, with this type of flow, so the game only needs to know its own contracts, and from settle and out, the information comes from a different path. I'll show you. Okay, so for the game, what I did is, instead of having a field per entity, so I have the MUX template as one field, and then an array for all the others. And then a selector selects the next template based on a value from the user. So you see something like selector, and then it goes as based on the select, it's mapping the selector index to the 32 byte space, and then it's gonna slice that specific template, and it's gonna validate we send to it. So it becomes more nuanced already. there's all kinds of like micro optimizations of how to encode a lot of workers, and now because there's a cost, it was natural to put all of them in one long array here and choose according to the location, like a natural choice, and it reduces the number of fields in the state, which makes the compiler a little more happy and stuff like that. Okay, I wanted to say something about the league. So the league is kind of, the Genesis is going to create, maybe you see it better here. The league is Genesis is going to create like, I don't know, 10 UTXOs of the league. And these UTXOs are only used in order to register players with the correct contacts. So a player is going to register to the league, and the transaction of registration is going to output the same league object and a new player, player A. Then player B is going to register into the league, and it's going to again output the same league so others can use it, and player B. Then player B and A start a game, so there's going to be a transaction consuming 2 inputs of both players, and it's going to produce 3 outputs, the game, and player B and player A. At the beginning of the game, the only thing that is going to change in the player is that it's going to be marked that there's an open games, it's going to increase by 1. Then the game is played, it routes, so the game here would be the MOOCs. So then it routes to a worker, goes back and forth until the game ends, get to the chess settle. And the settle is the one who knows how to consume, create now a 3-to-2 transaction. It's going to consume itself, player B and player A, and it's going to update the ratings and the stake according to the winner. So that's like the full entity flow lifecycle.
Well, that's really impressive. So just to make sure everyone understand, each square, each rectangle here is a transaction. Well, not exactly, but each
No,
arrows,
it's a UTXO.
Yeah, each UTXO. Sorry, yeah. That's really impressive.
A transaction is a little abstract here. Like the transaction here, player A, like this, yeah, player A and B. So the start game transaction. It's marked by the name. It's going to produce the game and the player A and B this way. So if we look at like the code, so let's look at the code of the league, for instance, is going to do a few things. One of them is it's going to verify the signature of the player. You don't want to allow a player to register with a stall PK. He has to prove ownership, otherwise he cannot play, essentially. Then we give him a unique ID. We use the outpoint trick. So we use introspection to read the outpoint transaction ID and the outpoint index. And yeah, it's going to be unique because of this line. So this is going to be a unique ID. I was just thinking for myself if it's safe in terms of the fact that a few players can register in the same transaction and get the same ID, but no. So essentially, because the outpoint of the previous input is unique, so the player ID is going to get a unique ID. So we don't need to have anything rolling in the league state. Like without this mechanism, you would need to have the league have some kind of rolling index, and then the league would have a mutable state and not immutable. So this helps the league stay immutable, which is nicer. So then the league creates the next player, provides its own template just in case, the player template, the MUX template. So essentially, a player must know how to play the game, right? So because game is going to be created by players, they must somehow carry the information of all contracts of game. And the way I did it, instead of having the league holding all the long 288 hash array, it holds the commitment to that array. and we only expand that commitment when we need it. Owner, player ID, open games because it's a new player, base rating, and then there's no other statistics. And then we use the like here, this line is essentially saying the league is unchanged. So because the league is immutable, we don't need to do complex P2SH, which is what you do when you have just validate output state. So you can just compare the public key, right? We also don't want a player registering to take value out of the league UTXO, so we make sure it's preserved. And then we make sure that there's a new output at index 1 with the next player information and the player template. So that's the league. Then the player has multiple entry points. Yeah, it's like the player is like a 2 to 3. So one of them is going to do the logic, the other is only going to delegate. That's the delegate start game. So that's the start game here. So one of them is going to execute the full start game. The other one is only going to make sure there's another player that's doing that. And then the other functions the player needs to know is how to settle. And in settle, it actually delegates. So what's going to run the actual settle logic is chess settle, and the player is only delegating. And then a few just utility functions, like I want the owner of a player UTXO to be able to change the value of the Caspa in it. So it's just a rebalance, which doesn't look at the value, but looks at verifies a signature. And the player can retire only if he has no open games. So that's how we make sure that no one can just abandon the arena without paying the price. So this works. Oh, I wanted to just do that kind of thing.
Maybe just a quick question regarding this relation to covenants. So we have here a covenant, which is the game covenant, one ID for the MOOCs and all of the relating logics, different contracts, one covenant ID, correct?
Yeah, one covenant ID, it starts with the league. So if the league, I don't know, 10, well, I wanted to make the league permissionless. So when you create a UTXO for the league, there's an admin, but it can never consume it doesn't have the option of consuming the UTXO and shutting it down. So once you create a UTXO, as an admin, you can try and extract Caspa value from it, but you have to keep that UTXO live. That's a logic you can see. Yeah, I allowed forking all the entry points in the contract of the league. Make sure that there's an output also by the league. So that makes sure that you can't close it, even if you have admin. So the admin can only control the Caspa value in the league UTXO, which is just convenient, but never used for the league maintenance. So when you create the league, you create like a number of UTXOs. You want to allow multiple players to register at once. And then that Genesis operation defines the covenant ID. And the covenant ID is then carried by any transition of the all contracts verify that the outputs, which also declare the covenant ID, are following the rules according to that contract. So it's always like a closed system of logic. So it's essentially a multi-contract flow system, complicated enough system. And even if it would be more complicated, you would be able to break the logic into multiple contracts, essentially. So I don't see a clear limit on the expressiveness of this system, of any system. Obviously, it has some cost in terms of scripts running on Caspa. Eventually, we'll have a fee market, I guarantee. And it's not going to be easy to run script of the size 5 kilobyte, but it's still pretty powerful. in terms of expressiveness. And anything that belongs to this peer-to-peer mindset of state, like chess, like assets, like anything like that, which is more peer-to-peer and not a single shared state which has a lot of contention, it is a natural candidate for developing above covenants. This is actually just a small local web app showing it's not only just talk, but it's actually a working game. So I'm not going to play a game, but it is. Essentially, this part I allowed Codex to do more freely, develop like an orchestrator and a game monitor. So the goal was to develop like an engine which can only watch transactions belonging to that covenant ID and actually understand, by knowing the game or knowing the contracts, understand from the transaction what happens. Because the transaction by design has to know the state, the output state, right? Transaction, in our case, if it's well defined and written correctly, part of its execution is to verify the output state. So somewhere in the execution, the data in the transaction reveals the output state. So if you want to be a system or an indexer following this chess league, and you know the chess contracts in chess games, there must be a way for you to look at each transaction executing on chain and understanding the state of the outputs, even though it's not necessarily in plain sight, right? Because the outputs are obviously a hash of a script, which is also includes the contract and the state. So you can't look just at the output and see what the state is, but there must be a way to do it from just looking at the transaction and executing it. There's no privacy here. So you can write a decoder that with enough knowledge can decode this class of contracts or this covenant ID. In general, going further, I can imagine maybe a system where you can provide a plugin for understanding a specific type or a specific covenant. And it can work in conjunction with Silverscript. So Silverscript can help you take the contract, the source code, and run it in a way that if you have the input argument of the signature, you know how to extract the outputs. Essentially, it's all the information is essentially there. So with support from the compiler, you can actually write maybe a generic enough system that doesn't need to know the intrinsics of every contract. I know for sure that it's possible to just parse or process the contracts and transactions and come out and understand what the output is, as long as they are well defined in a correct way. A lot to digest. It's getting pretty late. What do you think? I don't mind going on a little more. Maybe let's look at questions because. So what BitCat asked about, maybe it's answered or not, but he asked how it can get stuck. So because a move is composed of two transactions, you're moving from a MOOCs contract to a pawn contract. And if we don't verify enough starting conditions in the MOOCs, we just trust the user that this move, so-called, that he knows how to complete the move. So that's where it can get stuck. He can say, okay, this is a pawn and I want to move it to here. And really there's no pawn there, or the move is illegal. It's not a pawn move. And then the pawn contract is going to reject any attempt to advance because it's going to say, no, this move is illegal. This move is illegal. So you cannot go back from the pawn contract to the MOOCs anymore. But because the user signed the transaction, so we're telling him, okay, you signed this, it's your problem, you're stuck. So there's going to be a timeout, and the other opponent, the opponent is essentially going to claim the win. So that's how we avoided in this. This is like commit settle 2x atomic operation. Yeah, Grasp of facts, yeah, that's a good description. I wanted there's another angle I wanted to share about the chess, not so technical, about how to develop such a game, and it's related to what Ori showed before about the witnesses and the fact that we try to avoid the script from sweeping over all inputs and looking for that covenant, right? So we give it a witness because the script is essentially saying, I only need to see one. I need in any condition. If someone can show me the any, that's best. I don't need to search for it, right? So this mindset comes over and over when you try to do something like chess, because chess is so complicated. And if I would develop chess just normally, I wouldn't be able to develop it because like many moves have to check that the king is not on the threat now. So how do you check that? You have to check all, you might need to check multiple paths. Like if I moved my piece, so I must check that there's no threat from many angles. Not only one movement that I'm showing. I have to show no threat. I have to show checkmate. I have to show the king cannot move without being eaten. So what I did is bypass all that in a sense that this chess game is such that if you're an honest player and the opponent is not playing right, you can always win according to normal rules. It's not like there's no compromise on the game. If you play it, you can win whenever you're supposed to win. But the way the on-chain rules happen is like, for instance, checkmate is a simple example. If there's a checkmate, why do I need to make the on-chain covenant contract search for all the moves and say, okay, this is a checkmate? I'm saying, okay, this is a checkmate. If the opponent agrees and surrenders, acknowledges the mate, so good. If he doesn't, I tell him, okay, show me it's not a checkmate. Make a move. He makes a move. I eat the king because it was a checkmate. And by taking the king, I prove to the game I won. So I can always prove to the game I won. That's the simple example. There are other more complicated rules where I had to do more complicated stuff. Like when you castle, chess, the rule is you cannot castle if any of the squares the king is passing by is under threat. So an illegal castle needs to, essentially a castle needs to prove that there's no threat along the path. And that's, again, a sweep, which I wanted to avoid. So what I did is you do a castle, and then the opponent has the chance to challenge the castle if he wants to. And once he commits to challenging, he either succeeds and the other guy loses, or he cannot show it, and then it's a false claim, and the other one is gonna win because of a timeout. So you always flip it. Same thing for a draw when there's no move I can make. A claim draw. Like if I'm not under check, but I cannot move. So it's hard for me to prove it to you that I cannot move because I need to go over all possible. So I flip the game. I tell you, okay, I'm committing to the fact that I'm in a draw. You show me I have a move. So you get the right to play my pieces. And if you show me you have a move, I have a move. I can show you there's a king capture to do in that case, and then I prove my claim. And if I don't, you prove your claim. So essentially, you can go into challenge periods where the game is settled one way or another. So any normal rule off-chain can be enforced on-chain. That's like the type of thinking you have to adopt. And they can't, Bitcat, they can't happen in the same transaction because you spend one input and you send it to another output, and then that's how you want to execute that script owning that output. So you can't do that in one transaction. So you actually have to create a chain of 2 transactions, where the second one is spending the output of the first. That's how the move is actually going to look like. And in Casper, you can actually submit to the mempool like 2 transactions, and the mempool understands their dependencies as they're only going to inject the first one into the block, and then the second one is going to get into the following blocks. Only that's like an automatic. So in Casper, you can probably in other systems too, you can send like multiple or a DAG of transactions, and you always enter the block always get all those transactions which have no dependencies, like the frontier of the DAG of transactions. And then once they get mined, other transactions get into the frontier. So that's what's going to happen when you send this to 2TX. How did you do threefold repetition draw and the likes? So there's 2 rules I didn't implement yet. One of them is the 50 move draw, which is if no soldier, if no pawn moved and no tool was captured, no piece was captured, then the game can be drawn. So that's an easy one, but I just didn't implement it yet. Threefold repetition, if it's about threefold repetition across the game, like if the same scene happened 3 times in the game, so we can't implement that normally. So we have to give up on that. Like that requires full memory by definition, I think. So not something we can do. By the way, Jonathan has asked for a feature. He wants a special feature for this chess game. So I see this chess game as I'm gonna ask for the help of the community to deploy it, but I think we should actually deploy this on mainnet and make it a serious game arena. I mentioned before, yeah, you actually can, when you start the game, you can lock Caspa in the game UTXO, and then it gets settled according to the winner, so that you can actually pay for the stake. You can play on money, which obviously brings up the question whether someone can just put a computer against you. But that's not my worry to make at this point. I think you can play a game against some other players with reputation or whatever, but it's yeah. What Jonathan asked for a feature was he wants one ticket per game to split the game. Okay, we're doing something, and I have 2 options to do, and I'm not sure about them. So I'm telling you, okay, let's play 2 possible scenarios. Let's take this board, duplicate it. I'll do one move here and another move here, and we can split the stake, for instance, between the games. Obviously, this can blow up if you do it too long, but if you allow one or 2 a game, it can be a very interesting feature where someone can say, okay, it's too divided here. I want to, and that might be a unique feature for chess over CAS. How do covenants choose whether the rules of a game are clear enough? What if I had a game where the rules were messy? Would the covenants? So proof of work. So Audi, yeah, as a designer, I think you might be able to categorize, if you're a computer scientist, you might be able to categorize this messy game you're describing as in a class where the space required for the computation is not const. Meaning, if the logic is such that at some point of verifying the transition function or the logic, space requirements need to grow beyond the constant and it's unpredictable. So in one way or another, you wouldn't be able to probably wouldn't be able to do it on a covenant or become tricky. You can Merkelize state. You can make a tree of state and only reveal parts of it every time. I do that in some form or another in the game, but there is a class of games or covenants you cannot implement, definitely. I don't know exactly which. I don't know how to categorize it clearly enough. Fletcher, you want to go up? you can open a mic and just let's see if I can show anything else this that might shed more information. The rating function is a bit is an approximation. It was like an ELO style rating, but it's the formula itself is floating point. So I used a bucket approximation. It's yet to be proven correct. Yeah, so the chess example shows a multiplexing design. So it shows template injection and secure contract family bootstrapping, which I tried to explain, but I'm not sure I followed through. It shows the MOOCs worker multiplexing for bounded verification. It shows a multi-role covenant systems under one family. Timeout escape as liveness primitive. By the way, timeout as a blitz chess primitive, which is only possible in a high frequency system. That's essentially it might be one of the first motivations I had to do chess was blitz, because I think, okay, what can show the frequency of the system? So if you want to play a blitz chess of 10 seconds, hardly you need a very system with a fast clock, and we know one. So these are the contracts, and then you have the game family, transaction flow. Yeah, that's exactly like Fresher is saying. All these block-DAG properties is kind of what makes it interesting. You can try and not going to gain much of it, but you can try and send a double spend, like making two conflicting moves. I don't know what double spending bullet chess. Interesting things can come out of it, but yeah, we have to accept them as the strength and not the weakness in this context. Okay, I don't know what. We can obviously talk for hours, but
I think two interesting things to note here is that we have relations between different covenant. One covenant can be many kinds of contracts, because we started from Silver script and we can create contracts. And you showed how one covenant can be state machines of different contracts that are deployed together and working together. And then you showed another layer that we can create other contracts or covenants that knows about other ones and
the ICC.
enforce. ICC, yeah, this is the name.
So if you had a native asset and you wanted to make chess the owner of a native asset, so naively, how would you do that? So chess, because chess has many entities like a league, and it would be relatively easy if chess is unaware of DOG20. Then it would be relatively easy to add a chess operation to the same transaction as a native asset and claim that chess approved it. So if the chess operation has a signature verification, So I can imagine two covenant families authorizing one another without them knowing of each other, as long as one of them verifies the other is the owner and is existing as an input, and that input must have a signature, a kind of Schnoll signature. So the power of a signature is that it binds the whole transaction. Like the person entity signing the transaction knows about all inputs and all outputs. So you can create a system where covenants don't necessarily know exactly the logic of the other, but still, as long as for instance, I give ownership to chess only if I know that all chess contracts verify the signature of an entitled entity. And so if I'm the owner of the chess league and I know that every chess operation has to verify a signature of someone that's sufficient for me, so I am okay of putting my native asset under the authority of the chess league because I know how it can be spent only if someone actually actively signs a transaction with both chess a chess UTXO and the native asset UTXO owned by chess. So that's the kind of logic you can imagine. So I think ICC, and I'm understanding it as we speak, essentially, because we're really like discovering it. Not like this is a webinar about things we've grind over for years. This is like really what's happening. So I'm understanding it as we speak that ICC can support not necessarily. So I think the pattern is either one covenant knows about the other and essentially A authorizes B and B actually knows and looks at what's happening in A and verifies it logically. So there can be a one-way relation, right? Where A is saying, the native asset is saying, okay, native asset is A, and it's seeing the owner as B, and it sees an input of B spent. So, and it authorizes it. The reason the owner of B did this because either because B requires a signature, or because B is actually looking for inputs belonging to A and verifying some logic about it. So the authority can come either from inspection from the other contract, knowing something about the native asset contracts, or from signature like semantics. So it's an open design space. It's maybe too open now, but it's going to be more clear and more simple, and usability will emerge as the system matures. I feel like we're discovering something here. Like the whole we haven't explained what covenant IDs are, right? We kind of spoke above them, and I think the whole reason the multi-contract flow can work is because of covenant IDs. If instead of covenant IDs I had to prove lineage through previous transaction and grandparent transaction, this would blow up conceptually, wouldn't compile. So because we managed to simplify that layer, we kind of revealed that we can build more complex system above it now. That's the type of revelation we have now. Can covenant implementation allow web app and mobile apps deploy on mainnet? If not, there's any cancel drives. Of course, covenant implementation will allow a web app and mobile apps deploy on mainnet. What? I'm not sure I understand, but no, I don't think so. It's not the class of, no. Thanks. You can see the full. Wants to just look at it. I'm going to publish the book. I'll try to get, I don't know, I might need help and might not get to it in the next few days, but I want it to be deployed in testnet 12 if possible. And it showcases a lot. So I hope the main goal is obviously not chess. someone on X responded to my chess twit post saying, "Oh, that's what you like," with sort of like laughing at it. I don't think it's so funny. The joke is probably on him. This chess is a complicated system that illustrates something. And I already got like questions even before this talk about ideas for peer-to-peer systems above Covenant Caspa that I could tell the people, yeah, this is possible because I know I just have this POC. So it obviously illustrates something more powerful. That's it. I think I'm gonna fold. So that's almost 3 hours. I enjoyed. How about you?
I did personally learned a lot. I love this MOOC system. It opens great possibilities, and also so Ori previewed me some ICC possibilities. The way I understand it currently is a way to allow covenant execution or delegation of authorities in such a way I don't necessarily need to know in advance another contract, and I can allow its execution and delegate to him, whereas I would have need to know the contract in advance in full previously, if I understood properly. So I think that this is one major thing.
Yeah, the alternative would be nested execution. Like I execute a contract and then I see the owner of some operation as another contract, so I need to execute that contract. And that's not something you want to do in a script engine, like Ori explained. So delegating to the other input, which is a flat delegation, like a sibling delegation, makes a lot of sense. Actually, it was very hard to understand the pattern. I think Ori saw it first. But until SilverScript brings it to the surface in a normal way, you hardly can think about these principles through script engine opcodes. Too hard. It's too hard to think about these systems. So that's it. Yeah, so I got distracted from something. What did I want to say? Yeah, it becomes too hard to reason about just looking at script engine opcodes. You need to be Maxim for dealing with that. And when you see it in SilverScript and when you start implementing compiler macros that simplify the logic so you can actually start building something more complicated, because human beings think in layers. And also AIs and LLMs think in layers. And as long as we improve the layers and make them more and more abstract and more conceptual and clear, the more usage patterns will emerge above this. That's it. Okay. I'm getting off. It was a pleasure. Thank you, everyone, for staying on. Thank you, Caspero Labs, for developing this amazing studio. I didn't study too much yet, but it looks amazing, and I'm looking forward to you now understanding more of this system and integrating it. And thank you, Casperians, for all your tweets. And I don't know, many people here I appreciate. So see you all. Okay, I'm getting off. Bye.